All right, so step 4, we're at the end of this problem here. Let's grab what we did in step 3. Take that with us to the next slide. And step 4 says transform the solution back to the time domain. And so how do we do that? Well, we know that we can use the inverse Laplace transform to take a function of s, right? Inverse Laplace will give us a function of t, or I guess I should write it more like this. The inverse Laplace of f of s is going to give me my function of t. And we know that we can do this by doing that horrible looking integral in the s domain, or we can use the Laplace transform table. So what we need to do is we need to look for something in this form in the Laplace transform table. So let's look for 1 over s plus a constant squared in the table. So I'll go back to the table. The table is here. And if you look at this entry right here, it's 1 over s plus a constant squared. And so I'll go ahead and grab this, actually. Let's grab this, take it with us. Take a little screenshot there. That is our transform pair that we're interested in for this particular case. So let's get back to step 4. And let's take note of the fact that we can use this transform pair to solve the problem, okay? So our I of s is equal to 4, a constant, multiplied by 1 over s plus 5 squared. We know that we just need to take the Laplace transform of this and multiply it by 4, since constants just come along for the ride when we do these transforms. So the transform here is I of t is going to be equal to 4 multiplied by t e to the minus at times u of t. In this case, our a value is 5. So we just say 4 times t e to the minus 5t u of t. And that is our final expression for the current in the time domain. So we basically solved this entire circuit without using differential equations, because what we had to do was basically set up the differential equation, convert it into the s domain, solve it in the s domain, and then inverse Laplace transform to get us back to the time domain. And this is our time domain expression for the current in our original circuit, okay? And so the textbook actually has a picture of what this current looks like. Let me see if I can, it's going to take, let's just take a screenshot of it and I'll bring it over here into the slides. Actually, that's going to take a little bit of time. I'll just show you what it looks like roughly. So this is on page, if you want to take a look, this is on page 644 of the Eulaby textbook. Okay. And our current I in terms of amps, right, in terms of t, if we plot it over 1 second, 0.2, 0.4, 0.6, 0.8, 1 second, it basically ramps up to a value of about 0.3 amps, okay, just like this, at about 0.2 seconds, and then it just tapers off back down to 0. So this is our transient current here for this expression of time. If you want to take a look at this in the book, honestly, if you wanted to build this in LT Spice, you could also do that. That'd be a really interesting practice problem for you. You just have to model a switch closing or a pulse source that goes from 0 to 1.6. And you'll basically see that our current is going to rise up at the beginning and then taper back off to 0 in steady state, which makes sense. It should be 0 in steady state. Why is that the case? Because this circuit has a resistor, a capacitor, and an inductor in series, and a capacitor is an open for DC, right? So once all the transient behavior dies out here, we would expect there to be 0 current flowing in the circuit, okay? So I'm going to go ahead and end this video here. That's the 4-step process for how to solve circuits using Laplace transforms. And this was a very trivial case because we got a really nice answer for the quantity we were interested in that matches a Laplace transform pair very well. In the next video, we're going to talk about what we can do if we get to a point where we get our value in the S domain, but it doesn't look so nice and it's not so easy to transform. And that's called partial fraction expansion. So we're going to talk about that in the next video, and we'll see you guys in the next video.